Lesson 4 of Chapter 8. You recall Newton's laws of motion. One of those laws, the first one, says that an object that is in motion is going to keep on moving. An object at rest will stay at rest unless an outside force, we'll call it F, acts on it. And if it does, that outside force is going to cause that object to accelerate proportionately to its mass. This is Newton's second law, and this is for linear motion. Well, we have the equivalent or the analog of the second law in rotational motion as well. And that's what we're going to develop here and then apply. If you look at the picture over here on the left, you will see that we have an object M, and we have this straw of mass that is insignificant, but nevertheless rigid. And you can see this object is going to be rotating in the counterclockwise direction. And if it's going in the counterclockwise direction, that means that the vector representing the torque, if you take your fingers and curl it in the direction of this arrow going around, you'll notice your thumb points straight up out of the page, and that represents the vector for the torque that is causing this rotational motion. So down here we take Newton's second law, and what we're going to do is multiply both sides of the equation by the radius of the circle, the length of the straw. And then when we do that, we get this equation right here. If we remember this identity way back from, I think it was chapter 3, that we can convert our tangential acceleration into into rotational acceleration, or vice versa, using this identity. We substitute R A alpha in for A, and then we get this equation right here. Now you recognize that this term right here, a force that is applied tangentially, multiplied by the radius, is what we call torque, using the Greek letter tau. And this equation then says that the torque equals the mass times the radius squared times the angular acceleration. Now this term right here, mr squared, is going to be very important in this chapter. Mr squared applies just to this mass that is located and attached to the end of this straw of insignificant mass, and then the whole system is rigid. If we have other objects like disks or spheres or rotating things along other axes, we're going to get different values. They will all be something times mr squared. Some value x times mr squared, where x is 1, or often it's a fraction, and you'll see that in a little bit. So this equation then right here, at least for this ball that's attached to the straw that's rotating in the counterclockwise direction, represents Newton's second law in rotational motion. Now the mr squared value we often call the moment of inertia. And it's a term that's often used in calculus as well, the moment of inertia. And we're going to find that sometimes to calculate the moment of inertia, we can use straightforward algebra, like we did in this case. But if we have more complicated objects, especially when they're in three-dimensional space, like a sphere, whether it's a solid sphere or an empty sphere, we would have to use calculus in order to determine what the moment of inertia is for that object. You won't have to be doing that. On the AP test, you would be given the values for the moment of inertia for different types of objects. Once again, let's remember that when you are going clockwise, you have a negative torque. When you're going counterclockwise, you have a positive torque. All right, let's come to a torque on a rotating object. This time, instead of a ball that's located at a fixed distance from an axis of rotation, we're going to talk about a solid disk that is spinning. And indeed, a lab that accompanies this particular chapter, which you may or may not have done already, will be a metal solid disc on a horizontal surface that's free to rotate. Now, just like we said that the summation of forces when they don't equal zero must equal ma, we have the same principle here, that the summation of torques when they don't equal zero must equal the moment of inertia of the object times its angular acceleration. Because the disk is rigid and all of the objects we're looking at are fixed, they're not soft or sloshy like a thick liquid or anything like that, all the particles will have the same angular acceleration. When something is rotating like this, a particle out here and a particle there and a particle there, doesn't matter. They're all going to go through 2 pi radians in the same amount of time. So they have the same angular acceleration. So if we think about the solid disk as being made up of an infinite number of particles, M1, M2, M3, and so forth, and these at some distance from the axis of rotation, that's where we get the summation, the total rotational inertia or moment of inertia is the summation of the masses of all those particles times the distance of all those particles from their axis of rotation, all added together. And we use the moment of inertia. We use the letter I for moment of inertia, not to be confused with impulse that we had a while back. So the moment of inertia is defined. That's what the triple, the equal sign with the extra bar means. It's defined as a summation of all the masses times each mass's individual distance from the axis of rotation. And this is going to be different for different kinds of objects. Right now, of course, we're looking at a flat disk. Also notice that the units for the moment of inertia are k times meter squared. And this will be true regardless of what type of object is spinning or rotating. Kilogram times meter squared. So when we take I and we plug it in down here, now we have the analog. Instead of the summation of forces equal ma, the analog in rotational inertia in rotational motion is the summation of the torques equals inertia times angular acceleration. And keep in mind, I is going to be different for different objects, and I depends upon 2 things. I depends on the mass, which was all we cared about in Newton's second law in linear motion, but it also depends upon where that mass is located. In other words, how is it distributed? Is it all at the end, like the first example in the screencast with the ball at the end of a straw, or is it distributed throughout the object, like in a disk? So this is what we mean by Newton's second law in rotational motion. So on a test, if I don't give you this equation, and I tell you it's the same as, it's analogous to Newton's second law, which of course you should have memorized by now, you should be able to recognize that in rotational motion, my force becomes torque, and my mass becomes rotational inertia, moment of inertia, and my tangential acceleration or linear acceleration becomes alpha. So the angular acceleration of an extended rigid object is proportional to the net torque acting on it, just like the linear acceleration of an object is proportional to the net force acting on it. And again, the moment of inertia depends upon not just the quantity of matter, which we call mass, but it also depends upon the distribution of that mass. Now, if you take a look at these two objects right here, if both of these objects have the same mass, which is what's being talked about in 8.3, and the same radius and the same angular speed, can you answer this question? This is going to be a demonstration in class, which you may have seen already or you will see, depending upon when you listen to this screencast. Make sure you are able to not just answer this question correctly, but understand the answer. And of course, those of you that ride bikes are very familiar with the fact that we have bikes with multiple gears, and you can have a small distance to the axis of rotation with the smallest gear, and you can have a big radius or big distance for a big gear. And that's going to give you different quantities of torque. And of course, you need different quantities of torque when you apply a downward force on the pedal acting along this radius. You're going to need different torques based upon whether you're just starting up or you're already in motion or you're trying to go up a hill or you're trying to accelerate or slow down. You change gears. Back when my wife and I only had one car and we had 4 kids and she needed the car to take the kids all kinds of places, I did a lot of bike riding when I would do jobs during the summer. I'd just get on my 10-speed and I'd bike all over the place. And believe me, biking on Manchester Road is very, very scary. So, a little bit more about the moment of inertia. When we talk about a composite object, we mean the mass is distributed in all kinds of ways about some axis of rotation. And of course, you can also choose to rotate things on different axes of rotation. For example, you could rotate this baton from the very center, or you could choose to rotate it from the very end, in which case your inertia is going to actually be experienced differently. So, continuing on, with that long baton, we can come up with a different kind of equation for our rotational inertia. And in this case, if you recall where they were holding the hand right at the middle, you've got a torque there and a torque there. And if you're rotating this direction, you've got 2 torques. And so that's why we double the value right here. And there's my M is for mass. In this case, we're talking about the letter L instead of the letter of R. Doesn't necessarily matter what letter of the alphabet you choose to use as long as you understand what it stands for. So the moment of inertia, and this is about the 3rd or 4th time I've said this, depends on not just how much mass you have, but how is it distributed along the axis of rotation. So if you change the axis of rotation or you change how the mass is distributed, you're going to be changing the rotational inertia. Now here's a weird problem. I'm not big into baton twirling. I don't know how to do that. And I always thought the baton twirlers were maybe a distraction from watching the football game or whatever. But some of them are pretty amazing in being able to throw that thing up in the air and catch it on the way down and without hurting their hands. But here we have 2 problems. Find the moment of inertia of the baton about an axis perpendicular. So this dot, imagine it's coming out of the page into your face and going down into the page. You'll notice that it's spinning in this direction, which is clockwise. So you're going to have a clockwise torque that spins it in that direction. And clockwise means a negative torque. Then in part B, you're going to actually be spinning it on the edge of the baton rather than from the center. So let's look at part A. So in part A, we basically have 4 torques. We have a torque caused by this mass, by mass number 2, by mass number 3, by mass number 4. All of these masses are the same distance away from the axis of rotation, the center point, where the two batons are, I guess, welded together or something. And finding the rotational inertia of this rigid solid object then gives you a quarter of a kilogram meter squared. We do not have a special name for rotational inertia. It is the kilogram meters per second squared. We don't call it the Shaw or anything like that. Now, in part B, and we'll take a quick look at the picture for part B. So it's right here, and you're spinning it there. So there's your axis of rotation. And you'll notice that this mass right here and this mass right there, masses 1 and 3, are acting along the axis of rotation. So therefore, your torque arm is 0. So therefore, the torque caused by object number 1 and by object number 3 equals 0. So if we come back and take a look at the math down here, there's the 0 for the one part of the quadruple baton, or whatever you call that, and there's the 0 for the other. And you'll notice that the way you're spinning the baton in part B gives you much less inertia than the way you're spinning it in part A. In other words, you would feel it much easier to rotate the baton the way it is in figure B than it would be to rotate it in figure A. There's just not as much resistance to motion here than there is in the other way because the rotational inertia is less. And that's what it says in the remark right there. All right, calculations of moments of inertia for extended objects. What if we have a ring or a hoop like this, where all my mass is pretty much, is genuinely actually concentrated around the edge or the rim and nowhere in between? Well, once again, we can think about having an infinite number of masses. There's masses 1, 2, 3, 4, 5, 6, 7, and so forth. And the smaller we make the masses, the more accurate our final conclusion would be. You can see the calculus coming into play there. And you'll notice that we multiply all of them by the distance that they are, which is the capital letter R there. Each of their individual distances. And since all of these R's are the same, the sum of all those R's, the summation of all the R's, we're just going to call R, capital R. And that gives me then, for this hoop, for this disk, not for other solid objects, but uniquely for this hoop, my rotational inertia is the mass of the hoop times the radius squared. In other words, when I was talking about rotational inertia is equaling x times the mass times r squared, the value of x for the hoop is a 1. And the hoop is, again, another unique example. But there are many objects where you need to use integration in order to calculate what that rotational inertia is, or I should say to calculate the equation for the rotational inertia. And so let's go to table 8.1. And this is very important. You'll be referring to this in your homework, and you're also going to be using this information on the AP test and on my test. And these equations are going to be given to you. And notice the difference in all of these equations is basically the x. The value of x, in this case, is a 1. In this case, it's 2/5. In this case, it's 1/2. In this case, it's 2/3, and so forth. And this is how you find the rotational inertia. And again, the analog is my force in rotational motion depends upon where that force is located from the axis of rotation. The mass morphs into rotational inertia. The distribution of the mass is as important as the quantity of the mass. And since we're rotating, spinning on an axis, my A becomes alpha. Now I can further break this down so that my torque is defined as force times torque arm. my rotational inertia is some fraction times mr squared, and my angular acceleration is defined as the change in omega divided by the change in time. Change in omega would be probably radians per second. So if you think about this problem, you can see that we got a lot of variables in here. We have this variable, this variable, this variable, this variable. I already mentioned r. We have radians, and then we have time. And so you can imagine a physics problem on your homework or on a test, hint, hint, where you are given all of the values of these different variables except for one of them, and you have to solve for the other. So it would be very important that you can do this. Take Newton's second law, express it in terms of rotational motion, and then break it down into its component parts and plug your numbers in. Now here we have a weird example that I have never seen in real life, where a baseball player is loosening up his arm or her arm by throwing the ball without using the upper arm, but only using the lower arm. You've got the radius and the ulna. The radius is what enables you to rotate at the wrist, and the ulna, this is here's the radius and the ulna, and then here is your humerus, and at the end of the humerus, that bone, we sometimes call it the funny bone, because if you hit the edge of your elbow just right, you really get a twanging feeling that sometimes is painful. So you have the mass of your baseball here, you've got the mass of the forearm, and you have the distance of the forearm, and the speed of the baseball is 30 meters per second. It reaches 30 meters per second in 0.3 seconds. So 2 questions. Find the constant angular acceleration, excuse me, and then calculate the moment of inertia. And then the third problem is find the torque. So in part A, just like the final velocity of an object equals its initial velocity plus the acceleration times time, and if the initial velocity is 0, then basically you have the final velocity equals acceleration times time, which is basically the definition of acceleration, velocity divided by time. We use the analogous terms for rotational motion, rotary motion, and now we just plug our numbers in. If you remember this helpful conversion factor again, that velocity equals radius times omega, and you solve this for omega and plug it in over here. Solve it for velocity and plug it in over here. Here's my v over t right there. Here's my v over t. We get our angular acceleration of 286 rads per second squared. Now moving to part B in the problem, find the moment of inertia. Well, because the moment of inertia is a ball, and a literal baseball, acting at the end of a rod, which we're going to call the forearm, which is actually 2 bones, we're going to add up the total rotational inertia by finding the inertia of the ball and the inertia of the moment of inertia of the forearm, and just add the 2 together. So when you have a ball at the end of something, we use mr squared, and you can go back to the chart to look at that. If you have a rod that you're rotating around an end, an axis of rotation, which in this case is the elbow, and you look for that equation, your x value is 1/3. So we just plug our values in, the mass of the forearm and its length, the mass of the baseball, it's at the same length away from the axis of rotation, the elbow, and then we're going to add the 2 rotational inertias together, and that takes care of my total inertia. Now in part C, find the torque exerted on the system. Torque is rotational inertia times angular acceleration. So we take my total torque, put it in there, and we have our angular acceleration from part A right there. And now we can find the torque exerted on the system. And the torque is a Newton meter because of the fact that it is a force times a torque arm. Even though a Newton meter, if you remember the equation for work, force times distance, is also a Newton meter, we do not use the joule. The joule is exclusively used for Newton meters when we involve work, and over here we do not use joule because it's not the same thing, even though the units are the same. And a couple practical applications. The tall pitcher is going to have an advantage. A tall tennis player is going to have an advantage. Because being taller, they're going to have a greater torque arm, assuming they have the same strength as somebody who is shorter. Now, here's the hardest problem in this section, where we have an old-fashioned well, which some people still have way out in the country. I recall growing up where we would visit my uncle in upstate New York at Caroga Lake, and they had well water, and we had to take this well way down into the ground below the water table and bring the water up. Most surface water these days in most places is probably contaminated somehow by now from chemicals as well as animal waste. In any case, notice we have a solid, uniform, frictionless, cylindrical reel. In other words, a flat disc right there. So we're going to have to go to table 8.1 to find out what its rotational inertia is. We're given its mass and its radius. And in part A, we are drawing. And when you draw water from a well, you may not be familiar with that term. It means to pull water up from the bottom of the well in the bucket by rotating the handle at the end of the long pole, the axis of rotation, if you will, about which the disc, sometimes it's called a windlass, you're rotating that around. And you'll notice in this case, the direction is this way, which means if it was going the other way, you would have the opposite torque. One is going to be positive and one will be negative. So in any case, it says find the tension T in the cord, find the acceleration of the bucket when you're bringing it up. So this whole part is going up. And then in part B, the bucket's going to start at rest and it's going to fall. So part B, you're going down. That's going to make a big difference on the signs of some of your values, whether they're positive or negative. So now we do our free body diagrams. The first free body diagram is on the bucket itself. You have the tension and you have the weight. And if you think about it, if this is going up, if the bucket is going up, my bigger force, which is the force of tension, minus my smaller force, which is the force of weight, must equal ma. And this is for the bucket. Now, in the next diagram, this is the disc or the wheel that is fixed about the pole and it's going to rotate. And so it's in equilibrium in terms of up forces equal down forces. The upward force is the normal force, and the two downward forces would be the force of weight of that disc plus the force of tension pulling down. So the up forces equal down forces when you have, because you're at equilibrium at that point. And then you're also going to have some torques. Since you are bringing the thing up, your tension is going to be going up this way, and the weight is acting down. And so you can see here that the tension creates a counterclockwise torque, and the weight is going to be a clockwise torque. I think I got that right. We'll check that in the next section. All right, so we got these three unknowns. So let's come over here and start to solve the problem. Looks kind of messy here. So going up, to find the tension going up, here's my first condition of equilibrium, about the summation of my forces must equal ma when they're not equal to 0. And I take my bigger minus my smaller equals mass, and I can generate an equation. Then I look at my cylinder, and I go to the table, and I find out that table 8.1, the rotational inertia for a solid cylinder or disk is 1/2 mr squared. And so my condition of equilibrium for torques, since I'm not at equilibrium, then the summation of my torques, instead of equaling 0, must equal the analogous to ma, which is rotational inertia times angular acceleration. So my rotational inertia is 1/2 mr squared, my moment of inertia, times alpha. The next thing that we can do is, as we continue on, is begin to substitute some of these equations in for the other equations. So, for example, all of this right here is equaling this right here, and which is the force of tension times the radius, otherwise known as the torque. My torque equals the 1/2 mr squared times A. All I did was I took the torque equals I alpha, and I broke the torque down into force of tension times radius, and I broke my inertia down into 1/2 mr squared from the table, and then you have your alpha. And you'll notice that as we continue down, I can get my radiuses to cancel in where we have r squared and r. There's an r squared there. I can get that radius and this radius to cancel. And that and I'm going to write it right. I'm going to cancel it right there. That's probably a better way to show it. And so now I have this equation, and this equation is the same as this equation right here. Same equations. And then the next thing that we're going to do is to use this identity here, that my angular acceleration and my my angular acceleration and my linear acceleration are related to each other by the radius. And so my angular acceleration equals the actual acceleration divided by r. So I'm going to plug that in. And when I'm going to plug that in for this, and when I do that, the r's cancel. This r is going to cancel that r. And so now I have this equation right here, and that's going to come over there. And so now I can see that my total force, my unbalanced force, my force that's involved in acceleration, is going to be the weight acting down and the rotational inertia going in the same direction. And I can solve this for A, and now I can plug my numbers in to get my linear acceleration of the bucket going up. Then I plug this in back up here to negative 1/2 ma squared to solve for T, and then I get the tension on the rope. Now, when we're going down, all we need is this kinematic equation. You might remember it was distance equals initial velocity times time plus 1/2 acceleration times squared. And we're in the y-axis here, so we use y instead of distance, plug our numbers in, and you can see that if the level of the bucket, or I should say the top of the well is 0, when we are moving in a distance of 25.2 meters. And when we are, oops, I had that backwards, there we go. The bucket is going to go down 25.2 meters. So this is 0. When the bucket reaches the bottom, it's 25.2. And again, you'll notice it depends if it's counterclockwise or clockwise. Now, in a previous screencast, we talked about extending the system approach. And in the system approach, we ignore the internal forces, because internally, action equals reaction. They're all going to cancel each other out. We're only interested in the external forces. And those external forces depend upon the mass and the location of that mass. So if we remember that my rotational inertia equals mr squared for this disk, I'm going to double check that. Well, let's see, I'm not sure what object they're talking about here. Is mr squared. Then we solve this equation for m, and I get I over r squared. And so now we have, in a sense, two masses. We have the actual mass, and we have the mass due to the sense of mass due to the rotation of the mass about its axis, which is going to be right here. And we're going to add these two together and multiply it by A to get the total external force. So I over r squared is, it feels like a mass because it's hard to turn that when you have a mass that's not all located at the very center of the axis of rotation. So coming over here, in a sense, my summation of my masses, I don't know why I just did that. The summation of my masses times the acceleration equals my accelerating force, which is mg. What are my masses? The actual mass and the sense of mass because of its resistance to a change in position, my moment of inertia, and divided by r squared. Remember, moment of inertia is not mass. Moment of inertia divided by r squared has the same units as mass. And now I can come up with an equation that looks very much alike what we had way up here. So it's conceptually, it maybe is a little bit more complicated, but mathematically it's a lot easier to solve.